Welcome to Lab Tutorial Video 2. Today, we will cover booting and calling convention for finishing JAWS Lab 1. First, please check if you can get into the GDB debugging screen as follows. If not, please follow the following instructions. First, get into the terminal and use tmux to open a session. And by pressing a backtick and %, you can split the windows as in two panes vertically. And moving on the left side, run make QEMU OX GDB to run a runtime. And on the right side, run GDB. Then you can have the runtime pane on the left side and the debugging pane on the right side. And to examine how bootloader is running, for example, to start exercise 3, you can set a breakpoint at 7C00 and continue. Today, we will introduce how you can finish each exercise from exercise 3 to 8 for the booting sequence. After that, to complete the exercise 9 to 11, we will learn about how x86 calling convention works. Let's start with the exercise 3. The description says that set a breakpoint at 7C00 where bootloader starts its execution and trace through the code using the source code and the disassembly file. And also use x/i command in GDB to disassemble sequences of instructions in the bootloader and compare this with the disassembly and GDB. I will demonstrate how you can start this exercise. For example, you can get into the terminal and run tmux. So now I'm in a tmux session, and then at here run make QEMU OX GDB. And then at this time, we will open a new window on tmux by pressing backtick and C. So now the previous window is on Windows 0. By pressing backtick and 0, we can see that. And by pressing backtick and 1, we can move to the new window. And we will split this new window into two vertically, backtick and %. And then we will run GDB on the right side. And as the instruction indicates, let's set a breakpoint as 0x7C00 and continue. Then now our execution stops at 0x7C00. And then on the left side, let's open obj boot.asm. Then you can watch the GDB screen and the disassembly on the right GDB screen on the right side and the disassembly on the left side at the same time. And having this allows you to read the comments in the disassembly code as you follows the instructions executions in GDB. So for example, this assembly in GDB does not tell anything about more than like the name of the instruction, but you can also get some the idea of like what this instruction is doing. CLI clears the interrupt bit, so it disables the interrupt, and CLD clears the string operations direction. Yeah, something like that. And let's skip some of the easy steps, such as like enabling a 20 you can easily follow. Let's move to like how bootloader enables protected mode. So let's move to around here, about the protected mode, and let's move to line number 65, and the code for LGDT is at 7C1E. And to move the GDB context to that point, we can set a breakpoint to 0x7C1E and then continue. Then now we can see that our execution is at 7C1E. Then by following some of the instructions, so right now it will run load GDT. Yeah, we just executed with the SI command, and then it will move this value of the CR0 to EAX. So right now we didn't execute this instruction yet. So we can see the value of the EAX, which was a DF, and if I run SI, then that will be overwritten by the value of the CR0 register. Yeah. So that stored the value of 10, so it overwrite the EAX. And then we will learn or the CR0PE on bit to enable the protected mode enable bit, which is the value 1. Apply the OR to EAX to enable that bit. And because this value is 1, running up this instruction, yeah, we'll just add 1 at the EAX, so the value of the EAX will be 11 in hexadecimal, right? Yeah. And then we will put this value of the 11 of EAX back to CR0 to enable protected mode after executing the next instruction. Yeah. And then it will run a long jump to change the CS register. Yeah. And here, the value of our CS register is 0, but after running this instruction, this long jump, protected mode CS segment, which is 8, and the address of the protected segment, which is 7C32, is specified at here. Yeah. So right now, the value of the CS register is 0, and from the lecture, we have learned that the current privilege level, the privilege level of the CPU, is stored in the last 2 bits of the CS register, which is 0 for now. And then, by running this next instruction, yeah, through the command SI, yeah, we can see that the CS register and its value will be changed to 8. Yeah. And also the CPL of this value is also 0 because the last 2 bits of the 8 is 0. Yeah. So we just saw that like after JOS bootloader enables a protected mode, runs with the long jump to change the CS segment value and get into the protected region of the memory space. After that, to get to the point of running boot main, yeah, you may refer to the assembly lines here, and then search boot main on the disassembly, and now we know that the calling boot main happens at the address 7C45. So to see that, we can set the breakpoint at 0x7C45 on the GDB screen on the right side, and then continue. Then we are at the instruction 7C45, and there is a call instruction to boot main. And it seems like the boot main is located at the 7D0A, and we will get into that the function call by running the command SI. Now we are at the 7D0A, and let's also move the disassembly screen to 7D0A accordingly. Yeah, at here. Yeah. And to follow the process of the boot main, if you move your assembly code to this point, you may take a look at the C code, something like this line, and the corresponding assembly lines side by side. So for example, this C code calls the function readseg, and it will call function readseg with the argument of like a 10,000 as a ELF header, 1,000 as sex size multiplied by 8, and third argument as a 0. Yeah. So you can read about the assembly code and the C code side by side, and you can finish exercise 3 by continuing this kind of process. The setting after identifying, understanding, and identifying what the bootloader is doing, and moving the context of the GDB accordingly, and by matching like a two context back and forth again, you can find answers to the questions for the exercise 3. Next is about from exercise 4 to 6. For exercise 4, please understand why pointer.c works like as command specifies, and also read about the ELF header and the ELF file format from the Wikipedia. Doing such will be helpful for writing code in C and understanding how JOS loads the kernel to over 1 MB space from the disk, respectively. For exercise 5, you may edit the boot/makefrag file to adjust the starting address of the bootloader from 7C00 to 6B00 or something else. And then you can follow the BIOS execution to figure out at which point your boot process fails. And for exercise 6, please practice lots of the GDB commands for examining values and instructions. For example, to print values of memory as lots of hexadecimal integers, you can use the command x as examine 100 values and slash the size as a word, a 4-byte, each like a printing as a 4-byte each, and then in the format of hexadecimal as x. Yeah. And then put the address. So for example, x/100 wx. Oh, this like the number should be like placed after the slash. Yeah, it's a typo. Yeah, if you do this, like it will print out examine 100 4-byte integers in hexadecimal format starting from 7C00. You may try other commands by changing W to B or G to change the size of each printed integer. Or instead of putting X, you can put S or I to print the address as a string or instructions. Next, exercise 7 is for virtual memory access. If you follow the kernel assembly and the execution on GDB, you may see that the kernel tries to access the address starting from F at the top digit of the address. In lab 1, you can regard all the address starting with the F as a top digit, as a virtual address. So please figure out where JOS kernel uses a virtual address and an address starting with the F at the first time, and do the experiment by commenting out updating the CR3 register and put that instruction back. And for finishing exercise 8, you need to modify a lib/print format.c. And please refer to the case of the X and U. What it means is that, so you can open the lib/print format.c, and if you take a look at the case of X, which is for printing hexadecimal number, you can see that how it implements the printing out the hexadecimal number, and also in case of U, which is for printing an unsigned decimal number, and you can see like how you can implement the printing decimal number and hexadecimal number. And at here, please implement how you can print out by removing these 3 lines and then implementing it like these kind of the printing decimal or like hexadecimal number, please figure out how you can print out octet numbers at here. And then next is about exercise 9 to 11. You can easily find where kernel initialized the stack for exercise 9 from the source code and tracing the execution. So let's focus on exercise 10 and 11. The description of exercise 10 requires us to understand how C calling convention works within the function call with the test backtrace. Let's take a look at the function. In kern init.c, the kernel calls test backtrace with the argument value 5. And then take a look at the implementation of the test backtrace. And what it does is, like for a positive value of x, it will call the test backtrace function again recursively, but by decreasing the value of x by 1. So it will first call test backtrace 5, and then 4, 3, 2, 1, and then x will be 0. Then it will run mon backtrace with 3 arguments, 0, 0, 0. And the question is about how such a recursive function call is handled in the memory of the x86 architecture. And we will learn about this by learning how x86 computer uses a program stack. The following diagram depicts an example of x86 stack when running program in x86 processor. And the assembly code maintains all function arguments, local variables, and arguments to pass to make a function call, and the return address and saved base pointer are all stored into the program stack. And this stack grows down. Please focus on it. Although you have learned that the most of stack grows up in most of the other courses, at here the x86 program stack grows downwards. So it starts with the and this kind of stack is created whenever we make a function call, and this stack starts with the EBP address pointed by the EBP register, a register for storing the extended base pointer. And it ends with the address pointed by ESP, a register for storing extended stack pointer. And because stack grows downward, pushing a value is subtracting ESP by 4 and add a value on the stack. So for example, if our ESP is at the end of the argument 2, and if we run push argument 1, then it will decrement ESP value by 4 and create one's block space for the new item. And you may regard the width of the stack is always a 4 byte in this 32-bit machine. And then popping a value is adding the value of ESP by 4 to move up the ESP by 4 to set the stack new stack end as the one position up. For example, when we make a function call, my function in the slide, the argument passed from the caller myarg1 and myarg2 at here will be stored on the bottom of the stack. And then programs will store the return address somewhere in caller's address space where it just called my function, and that is the point where after the finishing of the execution of the CPU must return as 2. And it also stores the previous functions, the base pointer, And then to create the new stack context for this function, the code moves the ESP to this position. After saving the EBP to this position, after saving the EBP of the previous function. And then this function's stack starts at here, and it will be used for storing the local variables. And to do that, it will decrement the ESP to a certain extent to store all the local variables A and B and C, and also to pass the arguments to call other functions. It uses a stack, so it reserves the stack space up to accommodating like 2 more arguments. So this kind of thing is done by like decrementing the ESP register from the EBP. So at start, both ESP and EBP will point the same address, but by decrementing the ESP, x86 program defines the stack area of the certain function. So you may regard the EBP as the start of the stack and ESP as the end of the stack, and the stack grows downwards. And for the next, let's take a look at how x86 program actually manages the stack and the program. And to do this, let's debug starting from like a test backtrace. And to do that, let's set the breakpoint at the i386 init, and using the SI or NI, and you can follow the position. And to do that exactly, we can get the disassembly of the i86 init after you set up the breakpoint, and then break it there by running x/25i starting from the $PC, yeah, which points to the instruction pointer, yeah, and then it will show the disassembly of the code. And among the disassembly code, we can identify that there's a call for like a test backtrace, and right above the call instruction, we can see that it puts the value 5 at the address pointed by ESP. And previously I mentioned about like ESP always points to the end of the stack, and what this instruction is doing is putting the value 5 at the end of the stack. And then it makes a call to test backtrace. And calling a function, and what CPU does when we make a function call to a specific address is that it will push the next address of this call. For example, if we make a call at here, it will store the next instruction address, F01000 F4, as a return address. This is because after finishing running up to this function, our execution need to get back to this position and continue the execution. And to do that, and to handle that even for the recursive case, we store the return address on the stack before getting into the function. And there's no instruction to store the return address right after the call instruction, but that is done automatically internally by the CPU whenever we runs a call instruction. So the stack configuration before getting into the test backtrace will be like this. Okay, put 5 as an argument, and it will save the return address, and then we jump to the test backtrace. And in test backtrace, the first instruction it will run is push EBP. And I told you before about like the EBP will point to the start of the stack, but that was pointing to the start of the stack of the i386 init, the function that calls this test backtrace. And before we create a new stack by moving the EBP, the value, we first store the value of the previous EBP. So the the start address of the stack of the function in the upper level, yeah, on the stack. And then we move ESP to EBP, and the result of this will make both the value of the ESP and the EBP as the same, and the value of as the value of the ESP. So after running the second instruction, EBP will get down to this position. So this is completely okay because we saved the previous function's EBP, so we can restore this when this function returns. And then after that, it reserves some of the space, so it push ESI and EBX. So doing such will decrement ESP. And then internally, test backtrace will make a recursive call by decrementing its argument value x by 1. And to handle that, if you follow the instruction up to the point, there is a LEA instruction to decrement the argument value by 1 and store that to EAX, and then it will push EAX. So in this case, the value 5 will be decremented by 1, and the EAX value will be 4, and on the stack, it will store the argument 4. And then it will call test backtrace. So after calling test backtracer recursively, we need to store the return address of this function. So the next instruction of in the same function, yeah. So this F0100A1 is stored in here. And then our execution will continue at the start of the function, and the next instruction is push EBP to store the previous EBP to here, and move EBP down and also reserve a new stack for the another function. And the code will do this until the value reaches to 0. So it will nest this kind of the function call from 5, 4, 3, 2, 1, and 0. And please follow the executions of the kernel up to the 5 level of the nested execution, and please focus on how the value of the EBP and ESP changes, and how doing such can reserve a new space for the local variables and argument passing space for each function. And then when function returns, it executes 4 instructions from the stack. So for example, it will first pop EBX, so it will save the EBX, and pop moves ESP register 4 byte up. And then it will pop ESI, the second instruction, so it will restore the previous value of the ESI. And then, now our value of the EBP and ESP are the same. It will run pop EBP to restore the value of the EBP to the saved one. And then it will run return instruction, and the semantic of the return instruction is actually it pops EIP, but because the register EIP is not exposed to the assembly language at all in x86, so it is shown as a return. So what it actually does is it pops the value from the stack and store that to EIP, and it will directly change where we execute the code. And because we store the return address where the function returns to after finishing its execution, so popping EIP from here will make this function return to the position where we called the function. So this is how the x86 manages the stack, and then how the function call and returns creates a new context for the local variable and argument passing area, and then how return restores the stack. Yeah. So to summarize, EBP points to the bottom of the stack, the start of the stack, and the ESP points to the top of the stack. Yeah. And then at the address pointed by EBP, it stores the saved EBP. So if you get the address of the EBP as an integer pointer, a 32-bit integer pointer, and by accessing that as an array with index 0, that will read the saved EBP, which is the EBP of the previous function. And then you may get the value of the return address by accessing that array with index 1, and by accessing the EBP with the index 2, 3, 4, and 5, and on, you can get the first, second, third, fourth, fifth argument accordingly, which is required for finishing the remaining exercise of the lab 1. And for a hint on exercise 11, you need to print out all the backtrace, and to retrieve the value of the EBP, please use the function readEBP to get it. And when you retrieve the value of the EBP, please use the type integer pointer, because later we will use each of the data by accessing this EBP as an integer array with index 0, 1, 2, 3. And then for printing EBP, just printing this value, not the value in the EBP. That refers to the EBP of the previous function, not the current function. So to print out the EBP value at here, you can just print out the value that you read from readEBP. And then to print out EIP, this means that where the function should return to, so you can just print out the return address. And to print out this, use the value stored in the first, the index 1 of the EBP when it accesses as an array. And to print out the arguments values like these 5 values, you may print out the EBP value indexed, EBP as an array indexed from 2 to 2, 3, 4, 5, 6, to print out all 5 argument values. And then from this kind of the EIP value, you can get the information about these kind of the debugging information if you follow the instructions on the lab description page. And please do this until you see that the value of the EBP gets to 0. 0 means in C language is a null pointer, and we also use that value as having nothing. And that means there's no more stack frame. So please running a loop about the reading the current EBP and print out all these values, and move this the current EBP to the saved EBP and print out all the values for that, and again. And then when you get to the point your saved EBP stores 0, then stop at that point. And then I would like to introduce some of the coding convention that John's project follows. And some of them would be good to follow if you guys want to practice yourself for some of the standard for C coding or something. And for some of the things that I would like to point out is when you make a function call, please do not insert a white space between the function name and the argument list. So the upper example is the good one. There's no white space, and the example on the below is not a good example. And whenever you make not a function call but using of the if for while switch kind of the statement, please use add a one white space for if. By doing this, you can easily distinguish like a function calls from like this kind of the conditional the statement. And also because all of the like JOS naming convention follows like all the function name and variable names should look like all lower cases and having some of the underscore to replace some of the white space characters. And please use no camel case in case if you need to define a new function. And in JOS, all C macros are written in upper cases. For example, the function like the seg to create is the macro used for creating the GDT row for the global descriptor table. And from the naming convention, like all the characters are uppercase, then we can know that that's the macro, not a function call. And then whenever you use like a pointer types, please use include the white space before the making an asterisk. So you can regard this as a type name, and then like this is a pointer, and you can have the double pointer, triple pointer, and so on. And by representing that in this format, you can easily identify the type is this, and then it's a pointer of this type. And to add your own command, I recommend you to use like a double slash to add the command. And in some of the community, it disallows adding a command with double slash because in old days it is not included in C standards. So that is in like C++ standard, but not in C. So for example, Linux kernel still uses all comments as like a slash, asterisk, and asterisk slash. But because we in default, like some of the default comments written in like a JOS, which may be hint for you guys, are written in like this kind of syntax. If you use like if you write all of your command with double slash, then you can easily distinguish your own comments from like the comments provided by like us or like the originally prepared by the writer of this JOS project. And when you make a function with no arguments, please use a function name and argument list as a void and not f and the argument is empty. Empty here in C means like it could be any list of the arguments, and like mentioning about the void is more explicit to say that this function has no argument. And then another thing is like I believe that this could be useful for finding some of the functions in the project. I believe like many of you would like to know that where is the function, like in which file the specific function that you would like to look up is located at. And to help this, all the function definition in like a JOS is following the following naming convention. That is, it first specifies the return type and having a new line here. And then in the new line, the function name follows, and then argument list is specified. And by doing this, we can find where this function is defined by using this simple regular expression. So in terms of regular expression, this character means like a start of the line, and then if this name starts, this name is at the start of the line, then that will be definitely the definition of the function. The reason is, think about when we use this function, then we will have at least one of the function, and then in our coding style, we will have a brace and a tab. So when you call a function called for mon_kern info, then at least you will have a one indentation level before having a function name. So if you search the function name with regular expression, that as like the appearing at the start of the line, then that will always be the definition of the function. So for example, to find where this function is defined, then just run the grep dash n means like printing the number and name and the line number of the the line find it from the search, and R means like a search recursively from current directory. And then by putting the regular expression as like a starting with this function name, yeah, then it will also it will just finding like the function name start at the new line, and then it will print out let you know where the function is located in which file. Yeah. I believe like this will be very helpful, and you can like open this file and moving to this line number, and you can examine the definition of the function. And hope this helps you to finish up the lab 1. And please feel free to ask questions whenever I and our TAs are available on Discord. And thank you for your attention.